Okay, welcome to another Ginger Mathematician video. So this can be slightly different. I had a request for this, so I'm going to go through the iGCSE 0606 paper, which is the additional mathematics that Cambridge offer. This is kind of a mixture between the iGCSE courses, either the 0580 or 0607, and then the either A-level or IB courses. So it lies somewhere in between. And in terms of IB, I would say this kind of follows the standard level analysis and approaches course in terms of difficulty. So it's going to be using things like binomial theorem, for example, differentiation, rates of change, integration, things like this as well. So this is the paper in front of us. What's slightly different than the 0607 paper is that we're going to be using a standard calculator. So you can probably see it here. We're going to use a standard Casio calculator where necessary, but notice you do need to provide working for some of the answers. It's out of 80, you've got 2 hours, so that's pretty good time-wise, so 80 marks in 120 minutes. So it does give you a bit more time for thinking and working through the questions. Right, let's get started on question 1. So question 1 is on the axis below. We need to sketch the graph of y equals the modulus of x minus 2 brackets, x plus 1 brackets, x plus 2 brackets, showing the coordinates of the points where the curve meets the axis. So this is a nice way to get started with a bit of graph sketching. The way I always approach this whenever you see modulus signs is approach it as if they weren't there, and then we'll deal with the modulus signs at the end. So I'm going to think about this function first. So x minus 2, x plus 1, x plus 2. And the first thing to notice here that it's a cubic function. So if we're to multiply out all these brackets, we get a cubic. And it's a positive cubic because there's no negative x anywhere. X times x times x is x cubed. So it's going to be positive. So a general cubic, I'm not going to do it on this graph yet, a general cubic would look something along these lines. Okay, so it has, in general, not always, but 3 points where it crosses the x-axis and has this kind of shape. We'll look at this one in more depth about exactly how do I know which of these sections is bigger, because that's important to the question we are going to do. The first thing to do is highlight the roots or the x-intercepts or the zeros. You can call it lots of different things, and because it's in factorized form, it's going to make our life much easier. So we need to then think about what makes these brackets 0. So x is 2, because 2 minus 2 is 0. X is minus 1, because minus 1 plus 1 is 0. And then we have x is negative 2, minus 2, because minus 2 plus 2 is 0. So that gives us the roots of our cubic here. So I'm going to put down minus 1 and minus 2. Notice I'm kind of following what it says here, where the curve meets the axes. This is what I'm doing first. And then x equals 2, so we'll pop that over here. And then we need to find the y-intercept. And the way we find the y-intercept is we set the x to 0. So if I set the x to 0, again, I'm ignoring the modulus signs for the time being. Then we get minus 2. So imagine the x disappears, and the x disappears, and the x disappears. We get minus 2 times 1 times plus 2, and that gives us negative 4. So I'm also going to mark that on my diagram as well. So if we just had this cubic without the modulus signs, the graph would look something along these lines. And there's a few things to observe here. So first of all, we're going to come from the bottom and we're going to cross here. Notice this is not going to be very big because we need to get from minus 2 to minus 1. And then we're going to dip down to 4. And then we're going to come upwards like so. So this would be what my normal cubic would look like. Not entirely sure where the minimum point would be here. Again, that's something you could work out by differentiation if you so wish. But I'm just looking for a sketch. So now we need to think about, okay, it's got the modulus signs outside. So when it's outside the modulus signs, that means that everything has to be above the x-axis. So I'm going to put sort of mod outside. When it's inside, it has to be slightly more careful. Then it basically means that we have to always be above the x-axis. So I'm going to write that down to remind myself. So what that means is that this part of the graph here needs to go above instead. So I'm going to basically do a reflection of anything below the axis in the actual, and reflect it above. So -4, for example, gets reflected up to +4. For example, the roots stay the same because they're actually on the axis itself. So I'm going to try and draw this. This will be fun. Again, sketching was not always one of my best talents, but I got better at it over the years. So we've got here. Then we're going to go upwards, like so. Then we'll need to go downwards, like so, and then upwards, there. Okay, we do not know actually if this is the maximum. I need to move this across slightly, so I'm just going to rub this out a little bit here and just move it across. So again, we go down, we follow this graph, but that doesn't change because it's above the axis. And then we go like this. I want my maximum to extend slightly into this axis, and then go down and then up. So let's see if I can rub out the blue line now. And I actually get the graph that I'm looking for. Okay, so just give you the 3 marks. Just look at the mark scheme here. Okay, so yeah, pretty good. Yeah, I went up a little bit too far possibly. But yeah, it's a decent sketch. The shape is correct, x coordinates are all correct, the y coordinate is correct, and the maximum is in the first quadrant. Notice that 4 isn't actually our maximum here. So you do need to make sure the maximum goes into here slightly. You could verify this, don't have much time in the exam to verify this, by actually differentiating this function, expanding. But yes, the maximum is going to lie in this quadrant here. And if you're liking the content that you're watching currently, then please do consider liking and subscribing and sharing with your friends as well. Okay, thank you. Okay, and question 2. So the volume V of a sphere of radius r is given by V equals 4/3 pi r cubed. Yep, that's the volume of a sphere. The radius r centimeters of a sphere is increasing at the rate of 0.5 centimeters per second. Find in terms of pi the rate of change of the volume of the sphere when r equals 0.25. So the first thing I've noticed here, we've got rate of change. This is the phrase that I'm seeing here. So as soon as I think that, I'm thinking differentiation, and basically the way to go about doing this is to write down the information you have and see what you want to find. So first of all, we know the radius is changing with respect to time, notice per second, at a rate of 0.5 centimeters per second. So we're going to write then dr by dt, so that's the rate of the radius changing with respect to time, is equal to 0.5. So I'm just writing down the key information, so I'm going to tick that off. And we want to find the rate of change of the volume with respect to time. So it's usually implicit here, so when they talk about rate of change, it's usually with respect to time, so it's worth writing that in. And so we want to work out then what dv by dt is. That's kind of the question we want to answer. Now at the moment we don't have enough information in order to work this out. However, we can set up the chain rule such that we can work this out. To remind you what the chain rule is, it's working with another variable where you can simplify down to get what you want. So here, for example, we could actually work this out as dv by dr multiplied by dr by dt. Again, if you're not sure about this, this is called the chain rule that I'm using here. We do this at IB as well. I taught this to my IB high level group. On A level, I'm trying to think where it is. It's one of the C's, C3, C4, I think. The reason this works is, and this is really bad maths, but this might help you remember. Again, but mathematically this is not what's happening, which will make that very, very clear. Essentially, the dR's cancel, and I put that really inverted commas, and then you're left with dv by dt. Okay, so if we can write an expression for this, and we've already got this, so dr by dt, then we can actually work out what dv by dt is. Well, this actually isn't too hard to work out, so let me change my pen colour. dv by dr is the change of the volume with respect to the radius. Well, we already know what the volume is, yeah? We know the volume is equal to 4/3 pi r cubed. So we can actually differentiate this function, or this equation, to work out dv by dr. So just to remind you how we differentiate, we take the 3, we bring it to the back. So I'm going to write this out. So 3 times 4/3. Remember, pi is just a constant, it's just a number. And then we reduce the index by 1. So we're going to reduce this down to r squared. The 3's cancel. And what actually happens here, which is interesting, is that if you differentiate the volume, you get actually the surface area. This is the formula for the surface area of a sphere. So dv by dr is equal to 4 pi r squared. After that, we pop that into our chain rule. So dv by dt is equal to 4 pi r squared, because that's what we just worked out, times 0.5, because that's what dr by dt is. And if we do that, we just then get 2 pi r squared. So that's the general rule for the change of volume with respect to time, but they want us to work this out at a specific point. So in order to work this out, we actually need to put in r equals 0.25. So for this particular situation, we are going to pop it in. So 2 pi, and notice 0.25 is the same as an eighth. I tend to work in fractions. So a quarter. I know the answer is an eighth at the end, sorry. So we pop in a quarter, same as 0.25 squared. We do then 2 pi. Well, quarter times a quarter is a 16th, and then 2 times a 16th is an eighth, so we get 1/8 pi as our final answer, but we can also write this then as pi over 8, and we're done. I'm going to underline so the examiner knows where my answer is. I like working in fractions, they may want to work in decimals, I do not mind. Let's look at the mark scheme quickly. So 1 mark for recognising dr by dt, 1 mark for differentiating. Okay, did it the other way around, that's fine. And then 1 mark for the chain rule, applying that correctly, and then substituting that in, that then gives us the correct answer of 0.125 pi, which is pi over 8. Very, very good. Okay, and on to question 3, so a bit of binomial. So we're going to find the first 3 terms in this expansion, 4 minus x over 16 to the power of 6, in ascending powers of x. So we're going to go upwards, so we have the number, then an x term, then an x squared term, and so on. But we only need the first 3 terms, so that's going to make our life easier. Now fortunately, we do not need to remember the binomial expansion. You have this on your formula sheet here. I like the old notation as well. I'm not going to use the old notation. I think most people use the NCR notation instead, so I'm going to use that. So let's just now apply the formula to the function that we have. So the way I'd write this is 4 minus x over 16 to the power of 6. I'm going to use approximately equal to, because of course this is an approximation by using the binomial expansion. So the first term is always nice and easy. We just take 4 to the power of 6. So essentially we have n choose 0, and then we've got plus. So I'm going to use the sort of more modern notation here. So I'm going to use 6c1. You could write this as just 6-1. So 6c1, 4 to the power of 5. So we reduce the index by 1, but then we add in one lot of this. So minus x over 16. And because we have a minus in the middle of our expression here, it means we're going to get this kind of flipping idea of positive, negative, positive, negative. And then we need the next term, so we're going to have 6 choose 2. We're going to use a calculator to work this out, and then we have 4 to the power of 4, reduce the index by 1, but now we need to increase this one by 1. So it's going to be minus x over 16 all squared. And this is now where your calculator comes in. So 4 to the power of 6, that's 4096. If we work this out, so we get 6 choose 1, which is 6, times this, and then divided by 16. Of course, we're going to have a negative. Assumed it was positive. Because we've got a plus, this is going to be a positive number, negative. So positive times a positive times a negative is a negative. And then we get 384x. This comes from, this times this divided by negative 16. And for this one, 6 choose 2. Remember on your calculator, if you've got a normal Casio calculator like this, it's where the divide button is and you press shift and that will give you the option of 6C2. And if we work that out, remember that we've got a negative here but we're squaring, so this can be positive, minus times a minus is a plus. And then we also square the 16, so that gives us 16 squared on the bottom. And if you simplify all of that, you're going to give yourself 15x squared. Okay, so you can type this into your calculator sort of directly, make sure you've got the brackets there, that's really, really important. Now this is a nice classic question. I remember seeing this on A level many, many times. I think it's on SLAA quite a bit as well. I haven't taught it this year. And this is the magic word hence. So hence, find the term independent of x, i.e. the number, just a number or a constant. In this expansion, 4 minus x over 16 to the power of 6, which we've kind of started dealing with, x minus 1 over x all squared. This is where it can get a little tricky. So let me put the question up here. So what I'm going to do is I'm going to write our approximation from before. I explain why we don't need any extra terms. And we also need to put this part in as well. So if you expand this double bracket, remember x minus 1 over x is just a double bracket. Like so. We get x squared minus 2, because x times 1 over x is 1, minus 1 minus 1 is minus 2, and then we get plus 1 over x squared. Remember, minus times a minus is a plus. Now we need to take the approximation we just did from before. So 4096 plus 384x. That's minus. Did it again. I put a plus where it's a minus. There we are. Plus 15x squared. Now, of course, that expression could go into x cubed and x to the power of 4s, but because we want the term independent of x, say an x cubed term, it's never going to simplify to give you a number. X cubed times x squared is x to the power of 5, times it by a number is still x cubed. If you divide it by x squared, it's still going to give you an x term, not a number. So this is why we've just taken the first 3 terms, we don't need any more. Now what we need to think here is, if I was to multiply this out, so we use that sort of triple eyebrow, I like to call it, so multiply this by this, this by this, this by this, lots of lines, which can be quite confusing. What we need to essentially work out from all the lines I'm drawing in, let's use a different colour, is which ones give me a number at the end. So I've got 9 possibilities here, and I just need to work out which ones actually give me a number. Well, I think the most straightforward one is this number times this number. Yeah. So this root here I'm highlighting in green. If I multiply those 2 terms, minus 2 times 4096, that will give me just a number. Yeah, nothing else. The trickiest one also to notice is if I times this one, 15x squared, by 1 over x squared, that will also give me a number as well. Let me write this out. 15x squared times 1 over x squared. Now you can check this for yourself, but all the other combinations either give you an x or an x squared. So if I check 4096 times x squared, gives me an x squared. 4096 times 1 over x squared gives me 4096 over x squared. This one times this gives me x cubed, this one times this gives me an x, this one times this gives me an over x, and then this one here gives me x to the power of 4, x squared, and then the number. So these are the only 2 terms which actually give me just a number. Because in the second case, these two things cancel, and here we're just timesing 4096 by minus 2. So if I work this out, we get minus 8192 plus 15. And this is where we just use the calculator. We get minus 8177 as our answer. The key thing to realise in this question, this is where it's getting a little bit more tricky. This is just something you can expand, so you just expand it out. Then you think about the approximation we did before in part A. Think about which terms actually give us, just the number, just the term independent of x, doesn't have an x in it basically. When you get to higher levels at IB, it's easier if you can spot these things without having to do expansion, sort of thinking through, okay, what's going to give me the number, or what's going to give me the x squared term or the x cubed term, etc. So this is a good warm-up for IB and A level to come. Here's the mark scheme as well. So very straightforward for binomial questions. You get 1 mark for each of the terms. You get 1 mark for expanding it out like I did. 1 mark for writing down which ones don't have an x in and then putting it together. So straightforward mark scheme, you get 1 mark as you go through. Perfect. Okay, and let's have a look at question 4. So let's go to some combinatorics. So find how many different 5-digit numbers can be formed using the digits 1, 2, 3, 5, 7 and 8. Each digit may be used only once in any number. So I think the easiest straightforward way is that we've got essentially 6 numbers. We want to find all the 5-digit combinations. This is essentially just 6 factorial, which is 720. Alternatively, you could think of this in terms of permutations. So you could type into your calculator 6p5. So out of 6 numbers, how many different permutations of 5 can we get? Remember, permutations matter here. If you put the numbers in a different order, then that is a different number. This will also give you 720 as well. Nice 1 mark question. And then for part 2, how many of the numbers found in part I are not divisible by 5? Well, the only numbers that are divisible by 5 is one that finishes with a 5. So we take the 720 numbers that you can make with those 6 digits, and then we're simply just going to times that by 5 6, because 5 6 of the time the number will not end in a 5. So then we just pop that into a calculator. You can calculate it yourself, and then you are going to get 600, like so. So this is just getting you thinking about the question. Okay, not divisible by 5, that means anything that does not finish or ends with a 5 or 0. We don't have 0 in our list. So 5 6 of the time, the number is going to end not in a 5. Part 3 is a little bit tricky. There's a couple of ways you can approach this. So how many numbers found in part I, so out of the 720 numbers, are even and then greater than 30,000? So I'm going to start with even first of all. The only time a number can be even is if it ends in a 2 or it ends in an 8. So I'm going to write that as my 2 separate situations, which will add together at the end. So it ends in a 2, and then underneath I'm going to write here ends in an 8. So let's think, how many numbers end in a 2? Well, we're going to have 1/6, because only a 2 can be at the end. There's only 2 out of 6 numbers in total, times 720. And that's going to be the same starting calculation also for 8 as well, because it's the equal probability, equal chance. It ends with an 8. But this is where it gets a little bit tricky, because say it ends in a 2, let's put this over here, then we've still got the digits 1, 3, 5, 7 and 8. And then for 8, once we've got an 8 at the end, then we have the digits 1, 2, 3, 5 and 7. And this is now where the second part comes in. We want a number greater than 30,000. What's going to give us a number greater than 30,000? Well, it has to be one of these 4 digits right at the start of our number. Say I take 3 for example, it makes no difference what goes in the middle, 8, 7, 5, 1. Regardless of what these digits are, I can move them around, I'm still going to get a number greater than 30,000. If I apply the same logic here, then only these 3 numbers will then fit the bill. So I put in 7, then I can put any of the other numbers in whichever order I like, and I'm definitely going to get a number greater than 30,000. So for 2, this is where I have to be slightly careful here, I'm going to multiply this by 4/5, because there are 4 possible numbers out of 5, which will give me a number greater than 30,000. But for the 8, there's only 3 numbers that will give me, if it's at the start, give me a number greater than 30,000. So I work out the 2 situations, so I'm just going to do that now. So we get 1/6 times 720 times 4/5, that gives me 96. But for the 8 situation, 120 times 3 divided by 5 gives me 72. And then to work out how many numbers exist, then we just do 96 plus 72. And if we put that together, we then get the answer of 168, like so. Okay, and part B. So the number of combinations of n items taken 3 at a time is 6 times the number of combinations of n items taken 2 at a time. And find the value of the constant n. So as soon as we see this word combinations, we need to be thinking of that C function on our calculator. So the combination, so NC3, that's what the first part of the question is saying here, is equal to 6 lots of n items being taken 2 at a time. So that's going to be 6NC2. And from there we need to find the value of the constant n. So we need to go back to our formula sheet. So let's go back a couple of slides. And we actually have the formula here for NC2 and NC3. It's equal to n factorial over n minus r factorial, where n is going to stay as it is, but r is going to be 3 and 2 depending. So let's go back and pop that into our formulas that we have here. So we get n factorial over n minus 3 factorial is equal to 6 lots of n factorial over n minus 2 factorial. And we have to go and solve this. I just wanted to show you something that's probably going to be helpful to visualize here. So I'm going to write this on the side, and then once I've got the answers, I'm going to write them underneath. If I take the left hand side here, well, n factorial is equal to n minus 1, n minus 2, n minus 3, and we basically just keep going forever, yeah? It just goes on infinitely, etc. So I'm going to put that as dot, dot, dot. Okay, so this is the left hand side that I'm writing out here in the sort of longhand. The bottom would then be n minus 3, n minus 4, and it will continue in the same way as the top does. And don't forget our 3 factorial at the bottom. What you'll notice here is that this cancels with this cancels with this, and the whole infinite series cancels, and all we're left with is the top part. So n brackets n minus 1 times n minus 2 over 3 factorial. So I can rewrite the left hand side here as n open brackets n minus 1 n minus 2 over 3 factorial. And I can do a similar idea on the right hand side. So again, let's write this separately again. So I've got n minus 1, n minus 2 goes off to infinity and beyond, n minus 3, n minus 4. I think you get the idea, but it's just to show you how this simplifies rather than just going straight to where it is. The bottom then goes n minus 2, n minus 3, n minus 4, And then don't forget 2 factorial, still got that there. And again, we have this similar idea of the simplifying. So n minus 4 simplifies, n minus 3 simplifies, n minus 2 simplifies, and all we're left with is n brackets n minus 1 over 2 factorial. So let's pop that in. I'm going to put the 6 now at the top, so that's fine, just times in by 6, and pop it in the numerator. So n minus 1 over 2 factorial. Now we're starting to have something that we can actually work with here. So let's simplify this down slightly. We've got an n minus 1 on both sides, so we can cancel that from both sides. That's helpful. We know 3 factorial is equal to 3 times 2 times 1, which is equal to 6. So we get n open brackets n minus 2 divided by 6. And on this side, well, 2 factorial is the same as just 2, so let's just write 6n over 2. That can simplify further, so we get n open brackets n minus 2 over 6. 6 divided by 2 is 3, so we get 3n. And we've got something to work with here. So we're going to times by 6 on both sides. The rest is straightforward algebra. Equal to 18n and n squared minus 2n equals 18. And this is where it's nice and comfortable and you do your normal algebra stuff. And then we're going to minus 18n from both sides. That gives us n squared minus 20n equals 0. Almost there. I'm going to put this into a single bracket. The start of this question, that was the tricky part. And we're going to get 2 answers out of this quadratic. We're going to get n is equal to 0 or 20. And then let's just think about this. Having a combination of 0 items taken 3 at a time makes no sense whatsoever. So that's not an answer. Our answer is going to be equal to 20. And just pop up the mark scheme. So this comes from the previous question, question 4a. There were 2 different methods of taking on part 3. I decided to take the alternative here. I think that's easier to explain. And then finally, we've got the situation here. I did it like the first method here. But again, the alternative is very, very similar. Yeah, we're going to get a bit more cancelling involved, probably a bit more elegant. That is fine. Okay, stay tuned for more videos. I've finished now questions 1 to 4, and I'll continue with this paper. All right, bye-bye for now.